Okay, so in this video, we will cover the topic called L'Hôpital's rule. If you recall in this course, the first month was spent basically on studying limits, and then one great application of limits was finding the derivative of a function. If you remember, the derivative of f of x was the limit as h approaches 0 of f of x plus h minus f of x over h. So we've initially in this course used limits to help us find the derivative. Now in L'Hôpital's rule, we'll go backwards. We'll use the derivative, right? At this point, we know how to differentiate any function. And so we'll use our rules of differentiation to help us solve complicated and challenging limits. So we're flipping the limits and the derivative. We are no longer finding the derivative of a function with the limit. We will find the limit of a function using derivatives. So here's the statement of L'Hôpital's rule. The statement is actually quite simple, and very early on we'll extend it to more general cases. So let a be an element of the real numbers, but a could also be positive or negative infinity. So we'll write union, negative infinity, positive infinity. So this means that a, the symbol here means union, so or, so either a is an element of the real numbers, so a could be a real number, or a could also be negative infinity or positive infinity. In this case, we say a is an extended real number because we add to the real line negative and positive infinity. So this is our choice of a real number, or positive, negative, and positive infinity. And we assume that we have a limit that gives us a ratio of two functions. So assume that we consider a limit, say limit, as x approaches a, and the limit will have to be of the form f of x over g of x. So it is a ratio of two functions, and we ask what happens to the ratio f of x over g of x as x approaches a. And the assumptions are the following. To be able to apply L'Hôpital's rule, this must give either a 0 over 0 case, or it could also give a plus or minus infinity over plus or minus infinity case. And when I say plus or minus, I mean this could be positive over positive infinity, it could be negative over negative infinity, it could be positive over negative infinity, it could also be negative over positive infinity. The sign doesn't matter. So this is the assumption in L'Hôpital's rule. You have an extended real number in a, and you consider a limit of the form f of x over g of x as x approaches a, as long as you get a 0 over 0 case, or an infinity over infinity case. Here's what L'Hôpital's rule says. This is our only assumption. If the limit as x approaches a, and now, and this is the key result, we can replace the function on the numerator by its derivative f prime of x, and the function on the denominator g by its derivative g prime of x. You have to be careful, right? We don't differentiate the quotient using the quotient rule. We simply replace each function, the numerator by its derivative, the denominator by its derivative. And if this limit exists, or yields again a 0 over 0 case or infinity over infinity case, so if this limit, replacing each function by its derivative, either exists, so gives a real number, or yields again a 0 over 0 or an infinity over infinity case, then, and that's the conclusion, L'Hôpital's rule says that these two limits are actually equal. So the limit, as x approaches a, of f of x over g of x is the same as the limit as x approaches a of f prime of x over g prime of x. And that's L'Hopital's rule. So recall the assumptions. A is an extended real number. We look at the limit of f of x over g of x, and we have to have a 0 over 0 case or an infinity over infinity case, whichever the sign is on top and on the bottom. And when you consider this new limit, now f prime over g prime, if this limit either exists or yields a 0 over 0 case or an infinity over infinity case, L'Hopital's rule says that these two limits are actually equal. Before we consider examples, let's ask, why is this true? Now the general proof of L'Hopital's rule is quite complicated. We'll give here a simple intuitive argument in the case of a 0 over 0 case. That's why here I'll say this is really an intuitive feeling for why the result may be true. So we'll go with the heuristic argument. So assume we have a limit as x approaches a, and we'll assume that a here is a fixed real number of f of x over g of x, and we'll assume that we have, in this case, a 0 over 0 case. Let's see how we can transform this so that f of x is replaced by f prime of x, and g of x is replaced by g prime of x. As we've said before, though, the proof in full generality where a can be negative or positive infinity, and in these other cases, the general proof is much more intricate. But let's just get a feeling for it. So we have a 0 over 0 case. So we're saying that as x approaches a, f of x approaches 0. And as x approaches a, g of x approaches 0. So around a, f and g are 0. So we can let f of a being equal to 0, and also g of a to be equal to 0. Well, now we will subtract from top and bottom a 0. This may look silly, but so f of x is the same as f of x minus 0, but we'll replace 0 by f of a, because f of a is 0, over, well, g of x, and we'll do g of x minus 0, but again, 0 is equal to g of a. So this is g of a, sorry about that. And now here's where we'll be silly. As x approaches a, we know that x is close to a, but never equal to a. And so x minus a is not equal to 0. And so I'll multiply top and bottom of this fraction by 1 over x minus a. And let's see what we have then. We'll have the limit, as x approaches a, of, on top, f of x minus f of a over x minus a, all over the same expression now, but with g of x minus g of a over x minus a. But now think of what happens here. A is a constant, and now you have, as x approaching a, f of x minus f of a over x minus a. If it's not clear from the algebraic expression, let's try to visualize this graphically. Suppose the function for f looked something like this. The argument for g is the same. Suppose this is a, and just for the picture, we'll assume that x approaches a from the right. The argument would be the same as x approaches a from the left. So we have the point here and the point here. Now the y value here if this is the graph of y equals f of x, the y value here is f of x, and the y value here is f of a. And now we have the secant line passing through the point AF of a, x f of x. And the slope of this line, of course, is the change in y over the change in x. But think of it, the change in y is f of x minus f of a over the change in x, which is x minus a. So think of it, f of x minus f of a over x minus a is the slope of the secant line passing through the point AF of a, x f of x. But now we're letting x approach a. As x approaches a, this point will approach this point, and so the secant line will approach the tangent line to f of x at x approaches a. So f of x minus f of a over x minus a will be approaching the derivative of the function at a. And the argument is the same for g of x minus g of a over x minus a. This will be approaching the derivative of the function g at a. And so in the end, we can write this as simply as, well, what do we have here? We are letting f prime of x, x approaching a, and g prime of x, x approaching a. So we simply have the limit as x approaches a of f prime of x over g prime of x. If the derivative of f and g are both continuous, then as x approaches a, f prime of x will approach f prime of a, and g prime of x will approach g prime of a. So this is a sketch of the proof of L'Hopital's rule. In the case of a 0 over 0 case where a is a finite number, assuming that the two derivatives are continuous. But as I said, the general proof is more intricate, so we'll leave it to this heuristic argument. Let's now do some examples of L'Hopital's rule. Get a feeling for it. So number one, let's look at an old limit, and we'll solve it using a previous method, and we'll then solve it using L'Hopital's rule. So suppose we consider the limit as x approaches, say, 1 of x cubed minus 1 over x minus 1. As always, when we have a limit, we consider the case we are in. As x approaches 1, x cubed approaches 1, so we get a 0 over 0 case. So we have a 0 over 0 case, so here we could use right away L'Hopital's rule. Before we do so, let's go back to a previously used method. Whenever you have a ratio of polynomials, giving a 0 over 0 case, all you have to do is factor the polynomials. This is already fully factored. Let's factor x cubed minus 1. Since x cubed minus 1 is 0 at x equals 1, we know that x minus 1 is a factor of x cubed minus 1. Let's divide x cubed minus 1 by x minus 1. What times x is x cubed? That's x squared. Multiply, you get x cubed minus x squared. We subtract, and we get x squared minus 1. We repeat, what times x is x squared? So plus x, multiply, you get x squared minus x, subtract, and you'll get x minus 1. Plus, what times x is x? Plus 1. And so you get 1 times x minus 1, subtract, and you get 0. This completes your long division. Therefore, x cubed minus 1 is x minus 1 times x squared plus x plus 1. Let's see what that gives us. X cubed minus 1 is x minus 1 times x squared plus x plus 1 over x minus 1. And now, since x approaches 1, x is close to but not exactly equal to 1. So x minus 1 is not 0. We can cancel. And we're left with a very simple limit. The limit, as x approaches 1, of a polynomial, x squared plus x plus 1. As x approaches 1, so does x squared and x, so we get 1 plus 1 plus 1, and therefore the limit is 3. So we had the 0 over 0 case. It was the ratio of two polynomials. We were able to use long division to factor the polynomials, and after long division, the limit is 3. Let's now use L'Hopital's rule. Let's rewrite the problem. So we have the limit as x approaches 1 of x cubed minus 1 over x minus 1. As always, you can only use L'Hopital's rule if you have a 0 over 0 case or an infinity over infinity case. So looking at what case we have is crucial if we hope to be able to justify applying L'Hopital's rule. As we said before, we have a 0 over 0 case, so we can here use L'Hopital's rule. Every time you use L'Hopital's rule, here's what I want you guys to write down. The limit of this by L'Hopital's rule will equal to, and whenever you use L'Hopital's rule, write LH to specify that you go from here to here using L'Hopital's rule, and because we have a 0 over 0 case, this justifies that we are allowed to use L'Hopital's rule. The limit part stays the same, x is still approaching 1, and recall L'Hopital's rule, which said that you can, in the 0 over 0 case, replace the function on top by its derivative. The derivative of x cubed minus 1 is simply 3x squared. And you can replace the function on the bottom by its derivative. The derivative of x minus 1 is simply 1. And remember that the equality is valid as long as the new limit either exists or gives again a 0 over 0 case or an infinity over infinity case. But what we have here is trivial, because 3x squared over 1 is just 3x squared. As x approaches 1, x squared approaches 1, and this will approach 3 times 1, which is simply 3, as before using long division. So here we got a shorter solution to our limit using L'Hopital's rule. Let's look at another example that we could solve with that L'Hopital's rule. And then we'll solve it with L'Hopital's rule and hopefully, as we have seen in this case, arrive at the same answer. Let's consider the limit involving a square root. What if we let x approach, say, 4, and we consider the square root of x minus 2 over, say, x squared minus 16. Well, as x approaches 4, root of 4 is 2. 2 minus 2 is 0. So we have a 0 over, as x approaches 4, 4 squared is 16. Minus 16 will also approach 0. We have once again a 0 over 0 case. So we could use L'Hopital's rule, but instead we'll use an old technique of conjugation. We have a difference involving a square root, so we know the conjugation here will work. And at the same time, we'll factor this quadratic. So root of x minus 2 over, this factors as x minus 4, x plus 4. And now this is the conjugation part. We multiply by root of x plus 2 over root of x plus 2. Let's multiply out the numerator only. If we do so, we'll have root of x times root of x, that's x, plus 2 root of x minus 2 root of x, 0, minus 4. And we'll get a simple term of x minus 4 on top. On the bottom, we're left with x minus 4 times x plus 4 times the root of x plus 2. Since x approaches 4, x is very close to but not equal to 4. we can cancel the x minus 4 terms, and we're left with a very simple limit. X approaching 4 of 1 over x plus 4 times the root of x plus 2. Well, what are we going to have here? 1 over x plus 4 will approach 4 plus 4, which is 8, times root of 4 gives you 2. 2 plus 2 is 4. So you have 1 over 4 times 8, which is 32. The limit is 1 over 32, using an old method of conjugation. Because we had a 0 over 0 case, we know that we can use L'Hopital's rule. So let's solve the problem now using L'Hopital's rule. We read the limit, x approaches 4, root of x minus 2, over x squared minus 16. As always, we have to check the case that we are in so we can justify using L'Hopital's rule. We have a 0 over 0 case, which says that we are justified in using L'Hopital's rule. As always, whenever you use L'Hopital's rule, above the equal sign, write LH to specify that we go from here to here using L'Hopital's rule, which says that the original limit will be the limit of the new expression, x still approaches 4, and we replace both the numerator and the denominator by their respective derivatives. Root of x is x to the 1/2, so the derivative of root of x, which is x to the 1/2, by the power rule will be 1/2 x to the 1/2 minus 1, negative 1/2. And if you send the x down, it will be an x to the positive 1/2, but that's just a square root of x. The derivative of root of x is just 1 over 2 root of x. So we have 1 over 2 root of x on top, minus the derivative of 2, which is 0. So we have 1 over 2 root of x, over the derivative of x squared minus 16, which is 2x. And remember, when you use L'Hopital's rule, you don't differentiate the entire quotient using the quotient rule. You differentiate the numerator alone and the denominator alone. And then you take the ratio of the two individual derivatives. Let's simplify this a little bit. If you divide 1 over 2 root of x by 2x, that's the same as multiplying by the reciprocal. Therefore, dividing by 2x is the same as multiplying by 1 over 2x, which we can simplify as, well, 2 times 2 is 4. So we have 4x root of x. Well, let's see now. This will be equal to 1 over 4 times, as x approaches 4, therefore 4 times 4. And as x approaches 4, root of x approaches root of 4, which is 2. So we get 1 over 4 times 4, 16, times 2, 32. And we get 1 over 32, just as we did using conjugation. There you go. So we find the limit using an old method of conjugation. The limit is 1 over 32. Because we had a 0 over 0 case, we could use L'Hopital's rule. And we did apply L'Hopital's rule once, and we got to the same answer. Let's look at now examples where L'Hopital's rule will give us a limit that will not exist right away. And let's see if we can somehow use L'Hopital's rule more than once for a particular problem. So here's our third problem. Suppose we consider the limit as x approaches 0 of sine of x minus x over, say, x cubed. Now, here's an example where you will not be able to find the limit without L'Hopital's rule, right? Algebraically here, you can't simplify this, and the only techniques we had really as basic techniques of limits were conjugation, factoring, and some basic algebraic manipulations, none of which will work here. Let's see what case we're in. As x approaches 0, we get sine of 0, but sine of 0 is 0, minus x, which will approach 0. So we get 0 minus 0, therefore the top approaches 0, over, well, as x approaches 0, clearly x cubed also approaches 0, and we have a 0 over 0 case. And now here, as we've just said, we cannot solve this problem, this limit, without using L'Hopital's rule. Nothing we've seen so far allows us to solve this limit, but now we use L'Hopital's rule because we have a 0 over 0 case. So let's use L'Hopital's rule. The limit stays the same, x still approaches 0. Now we change the numerator and denominator for their derivative. Derivative of sine of x is cos of x, minus the derivative of x, which is 1, over the derivative of x cubed, which is 3x squared. Whenever you apply L'Hopital's rule and you have your new fraction, as much as possible, try and simplify it. Well, here it's already simplified. We can't simplify this any further, but if it were possible to simplify this, you would simplify and then ask, what's your case? But first, since this is already simplified, we can look at our case. As x approaches 0, we'll get cosine of 0, but cos of 0 is 1, and we'll have 1 minus 1, which is, again, 0. And as x approaches 0, 3x squared also approaches 0. So we have a 0 over 0 case again. So we still don't know what this limit is. It's still an indeterminate case. But if you remember, L'Hopital's rule says, as long as the new limit is either giving you a real number, so it does exist, or it gives a 0 over 0 case, or infinity over infinity case, the two limits, the old and the new one, are still equal. So you can say, well, what can we do here? We have a new limit, which is giving us a 0 over 0 case. Well, let's apply L'Hopital's rule one more time. The limit stays the same. X still approaches 0. And now we differentiate for the second time. The derivative of cosine is negative sine of x, minus the derivative of 1, which is 0, so we get negative sine of x, over the derivative of 3x squared, which is 6x. This is already simplified. Let's see what we get. As x approaches 0, sine of 0 gives 0, so we get 0 over 6 times x also approaches 0. So we have again a 0 over 0 case. So we still don't know what that limit is. It's giving us an indeterminate case. The question is, well, what can we do? Well, L'Hopital's rule says that if the new limit exists, or gives a 0 over 0 case or infinity over infinity case, it is equal to the original limit. So this equality is true. Well, we have a 0 over 0 case. What can we do but apply L'Hopital's rule one more time? X still is approaching 0. The derivative of negative sine is positive, well, sorry, the derivative of sine is cosine of x, so we'll get negative cosine of x, over the derivative of 6x, which is 6. What is our case now? As x approaches 0, this will approach cos of 0, which is 1, so we'll get negative 1. 6 is always 6, so as x approaches 0, 6 stays 6, so we get a negative 1 over 6 case. And here there is no ambiguity. The numerator approaches negative 1, the denominator is 6, so we get the limit of negative 1 over 6. And so there you have it. As x approaches 0, sine of x minus x over x cubed will be getting closer and closer and closer to negative 1 over 6. Using L'Hopital's rule not only once, but 3 times. So you can use L'Hopital's rule as many times as needed, as long as every step of the way the new limit gives either a 0 over 0 case or an infinity over infinity case. So you may end up using L'Hopital's rule 5 or 6 times. As long as you have the proper case, you can apply L'Hopital's rule as long as needed. And if you want to get a feeling for this, you can check this numerically. Set your calculator in radians. It has to be in radians because the derivatives that we have for trig functions are only true if the argument is in radians. And then compute, say, take x to be 0.00001, plug this in here, and you'll get a value that will be really close to negative 1 over 6. Let's do an example that would give us an infinity over infinity case. So what if we asked for the following limit? Number 4. Let's let now a be infinity. We'll let x approach infinity. And we'll consider the limit, say, x squared over the exponential function e to the x. Algebraically here, we cannot do anything. X squared is x squared, e to the x is d to the x. That's final. Let's look at what kind of case we have. As x goes to infinity, x squared goes to infinity. Now, if you remember, e is roughly 2.718. And so as x goes to infinity, you have a number here that is bigger than 2. And you take a bigger and bigger power of it. And so e to the x will also go to infinity. So we have a limit giving us an infinity over infinity case. You can, if you want, graph e to the x. The graph of e to the x looks something like this. When x is 0, the value is 1. And as x gets bigger and bigger and bigger, since we're taking a larger and larger power of a number bigger than 1, the values are getting bigger and bigger and bigger. We have an infinity over infinity case. We can use L'Hopital's rule. Recall L'Hopital's rule is applicable if you have either a 0 over 0 case or an infinity over infinity case. The limit stays the same. X is still approaching infinity. The derivative of x squared is 2x. And the derivative of the exponential function base e, the natural exponential function, is itself, e to the x. We can't simplify this any further. We look at our case. As x goes to infinity, 2x goes to infinity, e to the x still goes to infinity, so once again we have an indeterminate case. Infinity over infinity, but we can still apply L'Hopital's rule. X is still approaching infinity. The derivative of 2x is 2 over the derivative of e to the x, which is itself, e to the x. This is already fully simplified. And what's our case again? As x goes to infinity, 2 is always 2, it's a constant, over e to the x, which goes to infinity. And so we have a 2 over infinity case. Well, what happens to 2 if you divide it by something which is getting bigger and bigger and bigger and bigger? The fraction becomes smaller and smaller and smaller, so it will shrink to 0. And so the answer is 0. So by L'Hopital's rule, as x goes to infinity, x squared over e to the x approaches 0. So even though x squared is big, when x is big, e to the x happens to be much bigger because it kills the x squared term. And that's an application of L'Hopital's rule where the case was infinity over infinity. But you see, it makes no difference. Either you have 0 over 0 or infinity over infinity, you apply L'Hopital's rule in the same fashion, and x can approach even positive or negative infinity, it also changes nothing. One last example, and that is a word of caution. When you apply L'Hopital's rule and you get 0 over 0 or infinity case, sometimes L'Hopital's rule breaks down. In our next video, we'll consider examples where, even though we could in theory apply L'Hopital's rule, We shouldn't because we can do simpler. But here's one last example, and this is really a word of caution. Number 5. And like I said, in our next video, I'll give you more examples where you have to be careful about L'Hopital's rule. It's not a magic trick. Sometimes it will break down, and you can solve the limit in a really easy fashion without using L'Hopital's rule, but more basic techniques of limit. And this example will be such an example. What if we are letting x approach infinity, and we look at the ratio of x plus sine of x, the whole thing divided by x. Let's first find this limit using simple intuition, and then we'll ask, what if we apply L'Hopital's rule? And we'll see that L'Hopital's rule in this case breaks down. Let's simplify the expression here. Let's divide it through both terms by x. We have the limit, as x goes to infinity. Well, x divided by x is just 1, plus sine of x over x. Well, 1 is always 1 no matter what happens to x, so we can pull the 1 outside, and so we'll simply have 1 plus what happens to sine of x over x as x approaches infinity. Look at this limit now. Look at our case. As x goes to infinity, x goes to infinity. What about sine of x though? What happens to sine of x as x goes to infinity? Well, let's sketch this graph of sine of x here. Sine of 0 is 0, and sine is a wave function. It will oscillate always between 1 and -1. So the sine function looks something like this. It oscillates forever between 1 and -1, and of course the same if you go on the negative x-axis. So you see, as x goes to infinity, sine of x never approach a single value. As x goes to infinity, sine of x will forever oscillate between values that are between -1 and 1. So it will never stabilize and approach a single value. So as a single function, the limit of sine of x as x goes to infinity does not exist. The sine function will oscillate forever, and it will never approach a single value of y. But at least we can say that no matter the oscillation, it will never exceed -1 and 1. So what we have is always between -1 and 1. Now think of what we have here. We have a fraction where the numerator is never bigger than 1 in size, an absolute value. So you have a number that is always between -1 and 1, and you keep dividing it by something which is getting bigger and bigger and bigger and bigger. If you have a number between -1 and 1, and you divide that number by something that is getting bigger and bigger and bigger, the whole thing will just shrink to 0. So the limit of sine of x over x, as x goes to infinity, is simply equal to 0. You have a constant, or something which never exceeds 1 in absolute value, over infinity. This does shrink to 0. So in the end, we're left with 1 plus 0, and so the answer is just 1. As x goes to infinity, x plus sine of x over x approaches 1. And if you think of it, the intuition is the following. As x goes to infinity, sine just oscillates forever between -1 and 1, but x does blow up to infinity. So sine of x is insignificant compared to x, so you can ignore it, and really what you have is x over x, which is 1, and that's the intuition. Let's now see if we had tried to use L'Hopital's rule, if we would have arrived at an answer of 1. And you'll see that L'Hopital's rule here breaks down really quickly. before we can justify using L'Hopital's rule or trying to use L'Hopital's rule, we have to look at our case. As x goes to infinity, x goes to infinity. And now again, sine of x as x goes to infinity will oscillate forever between negative 1 and 1, but x does blow up to infinity. So if you think of it, if something gets bigger and bigger and bigger as big as you want, and you add something to it which is always between negative 1 and 1, the whole thing blows up as well. So we'll have an infinity over infinity case. Let's try and use L'Hopital's rule. It looks like it's justifiable, so let's see what we get. So we're trying to use L'Hopital's rule. We differentiate the numerator, the derivative of x is 1, plus the derivative of sine is cosine, over the derivative of x, which is 1. So all we have is 1 plus cosine of x. Well, as we did before, as x goes to infinity, 1 is always 1. So all we have is 1 plus the limit, as x goes to infinity, of cosine of x. Let's look at this limit and see what happens to it. And for this, we'll sketch a graph of cosine of x. Cosine as sine always is between negative 1 and 1. The difference is that cosine is a shifted version of the sine because cosine of 0 is not 0, but cosine of 0 is 1. And that's a graph of y equals cosine of x. And you see, we are asking here, as x goes to infinity, will cosine of x become closer and closer to a unique y value? And the answer is clearly no, because cosine of x as x goes to positive infinity, the y value, cosine of x, will oscillate forever between negative 1 and 1. It will never stop oscillating, so it never approaches a unique y value. Therefore, this limit does not exist. So look at that. If you add to 1 something which does not exist, the whole thing does not exist. So it looks like, if we're being careless, that the limit here does not exist, because we said the limit of this equals, by L'Hopital's rule, this limit which does not exist. So you might think, well, therefore, this limit does not exist by L'Hopital's rule. Well, right there you should be wondering, well, there's clearly something wrong here, because we know that the limit is simply 1. We found the limit directly without L'Hopital's rule, and the limit is 1. So we know it exists, and we know it's 1. So what's wrong in the argument here? We had an infinity over infinity case, we used L'Hopital's rule, and we said that this limit equals this new limit. But remember the argument in L'Hopital's rule. The original limit under L'Hopital's rule will equal the new limit only if the new limit either exists, gives a 0 over 0 case, or an infinity over infinity case. Well, this limit is not giving a 0 over 0 case, is not giving an infinity over infinity case, and does not exist. And so, this is not justifiable. This actually is false. And so L'Hopital's rule, in this case, breaks down. The new limit will only equal the original limit if the limit itself exists, gives 0 over 0 case, or infinity over infinity case. And here that's not the case because this limit does not exist. Therefore, L'Hopital's rule breaks down. So it cannot be applied to this problem. So that you have to be careful. If the new limit that you get doesn't exist, breaks down like this, or doesn't give a 0 over 0 or infinity over infinity case and simply gives you something strange like this, then L'Hopital's rule just simply breaks down. And you cannot conclude anything about the original limit. It simply does not apply. And you can see this because we knew the original limit was just equal to 1. So be careful about that. And one last thing to worth mentioning is that the limit here could not exist in a specific way, and that it could be positive or negative infinity, and that would be okay. Let me give you a simple example of that, just to make sure that when I say does not exist, I exclude negative and positive infinity. This would be the last example. This will be really short. So if I give you, say, 3 to the x over x, as x goes to infinity, 3 to the x goes to infinity, x goes to infinity, so we have an infinity over infinity case. We can hope to apply L'Hopital's rule, so let's try to apply it. X still approaches infinity. The derivative of 3 to the x, this is an exponential function base 3. That is the same function times the natural logarithm of the base over the derivative of x, which is 1. So we get the limit as x goes to infinity of 3 to the x times ln of 3. Ln of 3 is a positive number, it's a constant, it's positive. And as x goes to infinity, 3 to the x goes to infinity, so a positive number times something which goes to infinity goes to infinity. So you see here, the new limit does not exist, but in a very specific way. It does not exist in the sense that it goes to infinity. So here L'Hopital's rule does work out. The new limit does not exist, but is infinite. Therefore, the original limit is also infinite. If the answer were negative infinity, the original limit would also be infinity. So you have to be careful. When I said the new limit does not exist, I mean in the sense that it doesn't exist and it's not infinity or negative infinity. If the new limit gives positive or negative infinity after applying L'Hopital's rule, the original limit is also positive or negative infinity. So it does work out. But if the limit doesn't exist, in the sense that it's not infinity or negative infinity, then you cannot conclude anything about the original limit. You have to find, hopefully, a way around it. In our next video, I'll give you a few more examples of limits where, even though on the surface it looks like we may use L'Hopital's rule, but in reality we should avoid it. And you'll see either because L'Hopital's rule gives you a longer solution, or simply a solution is not going anywhere. This will be the topic of our next video.